In our last video, we looked at solving exponential equations, and if this works, it's the easiest way of doing it, and that is to try to get the same base, same number, to some power, and then we know that we can set our exponents equal to each other and solve. But that doesn't always work. For instance, let's say that we have 2 to the x power equals 35. If I multiply if I multiply 2 times itself repeatedly, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. I cannot write 35 as 2 to some power. I can't do that easily with an integer. So I'm going to have to use a completely different process here. Remember when we were solving logarithmic equations, we saw that if the logarithm base a of n equals the logarithm base a of m, then it's true that n equals m. And we could set our arguments equal. Notice that this arrow here goes both ways. It's also true that if n equals m, then the logarithm base a of n equals the logarithm base a of m. And that's what we're going to use to solve exponential equations, in other words, equations with the variable and the exponent, if we cannot get the base equal to each other. And moving forward, in our next lesson on applications, this is going to be the primary method that we use. What we're going to do is we're going to actually go in this direction, and we're going to put a logarithm in. I like to use the natural logarithm because it works best with base e, which we're going to use quite a bit in our applications, and the natural logarithm is on your calculator, so that means we can actually get decimal approximations of natural logarithms. So what we're doing here is if we have the original equation 2 to the x power equals 35, I recognize that it is an exponential equation because the x is in the exponent. I check to see if I can get the same base, which I cannot. So now I take the natural logarithm of both sides of the equation. And the benefit of doing that is our logarithmic principle that if the logarithm base a of n to the r power, that equals r, remember we multiply that r out front. So that's equal to r times the logarithm base a of n. We're going to use that principle. So what that allows us to do is back over here in our equation, this x is my exponent, so I can take that x and multiply it out front. So now I have x times the natural logarithm of 2 equals the natural logarithm of 35. And we have taken an exponential equation and made it into an equation which is plain old multiplication. The natural logarithm of 2 is a number. It really means e to what power equals 2. The natural logarithm of 35 is a number. E to what power equals 35. So this is just a number, and this is just a number. So to isolate x, because we're multiplying here, we're going to divide both sides. The natural logarithm of 35, divide it by the natural logarithm of 2. And I don't know what that number is, but you can plug it in on your calculator. So what you're going to do is you're going to use your ln key. It will open a parenthesis. Type in the 35. Be sure to close that parenthesis. Then do your division. Put in another natural logarithm. It will open a parenthesis, close that parenthesis, and then hit enter. And if I do that on my calculator, I see, and I'm going to just round it to the hundredths place, I see that I get 5.13. And that makes perfect sense because we know that 2 to the 5th power equals 32. So it makes sense that 2 to approximately the 5.113 power equals 35. If you plug that in on your calculator, if you plug in 2 caret 3.1, if you plug in 2 caret 5.13, you get 35.017 something. And that's because of a little bit of rounding error when we rounded to the 5.13. I'm going to write another problem and have you work this one. So let's say that we have 5 to the x power equals 275. If I multiply 5 repeatedly, 5 times 5 is 25, times 5 is 125, times 5 again is 625. We see that 275 is not an integer power of 5. So use the method that I just showed you to solve this equation. Pause the video, follow the steps in the previous example, and then start the video back. Okay, I know this is an exponential equation because the x is in the variable is in the exponent. I try to get the same base. I see that that will not work. So now I take the natural logarithm of both sides. And it's very, very important that you understand you are not multiplying by ln. You can't just have ln out in space. You have to specifically say the natural logarithm of 5x equals the natural logarithm of 275. Then that tells us that we can multiply our x out front. And this side stays the same. And then we can divide on both sides by the natural logarithm of 5. And then we can plug that into our calculators and watch out for those parentheses. It opens that one, so you have to shut the other. Do division, then a second natural logarithm, and we see that we will have natural logarithm of 275, close parenthesis, divided by natural logarithm of 5, close parenthesis, and rounding to the hundredths place, I get 3.49, which makes perfect sense because 5 cubed is 125. 5 cubed is 125, and 5 to the 4th is 275. 5 to the 4th is 625. So we knew that our exponent had to be somewhere in between those, between 3 and 4. Let's look at some examples where we have to do a little bit of work before and after taking the logarithm. Let's say that we have, we're solving for x here. Let's say that we have 10 times 3 to the 4x plus 1 power equals 572. And I'm thinking there's going to be no way I can get the same base on this one, so I'm going to be using the natural logarithm to solve for my variable in the exponent. But before I can take the natural logarithm, I have to isolate the piece with the exponent. Here I have 10 times the 3 to the 4x plus 1. So to eliminate the 10, I'm going to divide on both sides by 10. So I have to isolate the exponential part before I can do the natural logarithm. Now I can put in the natural logarithm. And remember, I'm taking the natural logarithm on both sides, so I have to be very careful how I write this. I'm not multiplying by ln. I'm taking the natural logarithm of 3 to the 4x plus 1, taking the natural logarithm of 57.2. Now, this is the same thing as this. So this part, this whole part here, 4x plus 1, is my exponent that multiplies out front. So I have to put the whole thing, 4x plus 1, in parentheses, times the natural logarithm of 3 equals the natural logarithm of 57.2 on the right-hand side. Now this is just plain multiplication. So I can divide both sides by natural logarithm of 3. Now I'm still trying to isolate x, so I subtract 1. And then now I can divide that whole thing by 4. And that looks really crazy. But it's important to remember the natural logarithm of 57.2 is just some number. Natural logarithm of 3 is just some number. So we can do this on our calculators, but we have to be very careful of our order of operations here. So we're going to type in ln, it will open a parenthesis, close the parenthesis, then divide by the natural logarithm of 3, close that parenthesis. And then I'm going to hit enter to get it to go ahead and do that division, get that number. Then I'm going to subtract the 1, and I'm going to hit enter to get it to go ahead and subtract the 1. And then finally, I will divide by 4 and hit enter to get my answer. It's important that you hit enter at each step to get it to do each step before it moves on to the next step. So if I do that on my calculator, I hit enter, minus 1, enter, and then divide that whole thing by 4, and I get approximately equal to, if I round to the hundredths place, approximately equal to 0.67. So what we saw in this example is that as we're working through, it's important to do each step in the correct order. We have to isolate the exponential part by dividing by 10. Then we take our natural logarithm. Then we multiply our exponent out front. And then we isolate x just using normal algebraic process. And as we enter that into our calculator, it's important to make sure that it uses the order of operations that we intend. Let's look at another example here. Let's say that I have this equation. and we're solving this equation. And we see that this is an exponential equation because the x is in the exponent. Now, my base on this side is e. The 0.04x is only affecting the e, not the 3,000. My base on the left is 5,000. There's no way I'm going to get those to the same base. So I know I'll be using the natural logarithm to solve. It doesn't matter that I have base e here. E is a number, just like 3 is a number, just like 5 is a number. So we're going to be using the same process that we used before. And our first step would be to isolate the exponential part. Notice that I have multiplication here, understood multiplication, between the 3,000 and the e to the 0.04x. So I will divide on both sides by 3,000. So I divide 5,000 by 3,000. On both sides. And I know that I am dividing because I have multiplication between 3,000 and the e to the 0.04x. And on my calculator, I see that I get 1.666667. And, repeating. I don't want to have rounding error. So I'm going to do math frac on my calculator and see if I can get that as a fraction. And obviously that is 5/3 because my zeros all canceled out. If you get a decimal answer, a decimal approximation, keep lots of decimal places so you do not have rounding error on these, or just leave it as a fraction. So we have e to the 0.04x. And now we're to the step where we can take the natural logarithm on both sides. So we have the natural logarithm of 5/3 equals, and we're going to see something that happens here on the right-hand side. If I take the logarithm base a of a to the r power, remember from our principles of logarithms, that really means a to what power equals a to the r power? Well, that's just equal to r. So if my base is the same, then when I take the logarithm, I just get the exponent. Well, if I rewrite this principle in terms of base e, remember ln means logarithm base e of e. So I have the natural logarithm of e to the r power just equals r. So when I take the natural logarithm of e to the 0.04x power, that's just equal to the exponent, 0.04x, because natural logarithm and e use the same base. I could not do that on the previous examples because I had natural logarithm of 3, not the same base. Natural logarithm of 57.2, not the same base, etc. This only happens if you have base e and the natural logarithm. So when I solve for x here, I'm going to divide both sides by 0.04 because this is understood multiplication. So I have the natural logarithm of 5/3 divided by 0.04 equals x. And if I plug this in on my calculator, be careful on this one because I'll have natural logarithm, open parenthesis, 5 divided by 3, close parenthesis, divided by. I do not have another natural logarithm. I'm just dividing by 0.04. And I can plug that in on my calculator. And get a decimal approximation rounded to the hundredths place. I get x is approximately equal to 12.77. When we first started this lesson, I told you that I chose to use the natural logarithm because it is on our calculator and can be evaluated on our calculator, and that we were going to be using base e in our applications. And as you can see, using the natural logarithm with base e allows us to just get to the exponent. I could have used the common logarithm in the first two examples and then typed in the common logarithm, log, base 10. But I could not have used the common logarithm on this one and gone straight to the exponent because the common logarithm and e are not the same base. Let's look at another example with e. I want you to do this one yourselves. All right. You solve this one, pause the video, look back at the previous example, and solve for x. Our first step is to isolate the exponential part. So I divide by 1300 on both sides. Then I take the natural logarithm on both sides. And the natural logarithm of e to the negative 0.07x is just negative 0.07x. Rewrite this. And then I can divide both sides by negative 0.07. And I get a decimal approximation of ln parenthesis, it opens its own parenthesis, 5 divided by 13, close parenthesis, divided by negative 0.07, and I get approximately equal to 13.65. So now we've learned how to solve exponential equations, in other words, equations with the variable in the exponent using the natural logarithm. And we're going to see in our next lesson that this will be very, very useful to us in our application.